All right, welcome everyone who's joining. Going to give folks a few moments to join and then we'll get started with a quick intro. All right, looks like we've got a good amount of folks hopping in the room. So welcome everyone. Thank you so much for joining today for When Green Turns to Blue. This is a new presentation from the team at Siplast, so we're really excited to be bringing this to you today. It's going to be presented by Rick Kile and Andy Watts from the Siplast team. My name is Bo. I'm here with Acelab. We are helping out with hosting today's event. Before we get started with the CEU, just while folks are joining, I'm going to give you guys some quick information on some steps and what will happen after today's webinar. All right, so I'm going to share my screen here. Everyone who signs up for a webinar with Acelab automatically has a free Acelab account. So some of you might have checked this out already. If you haven't, head to acelabusa.com after today's webinar. There's a ton of great free resources here for you. On the homepage, you can always sign up for our next upcoming webinars as well. Today, I just want to show you what to do if you know the manufacturer that you're looking for. You can always use the search bar in the top here, type in the name of any manufacturer or any product. That'll cross-search between product categories, brands, and other resources. Just make sure you're on that brands tab here. And you can head over to Siplast's page on Acelab. This is a great place to come after today's webinar if you want to get some more information. Get in touch with their team directly by clicking this contact button. Explore some more about their company as well as their products. And you can jump into any of these to access downloads, view performance data, and you can also save them to your projects or to your firm library so you can come back to this information later on. So this is a great place to come after today's webinar to get some more details on the products we're going to be talking about today. Other than that, I just want to show you folks, if you do let us know that you would like to get in touch with today's presenters for some more information after today's webinar, we'll go ahead and connect you with them over on your Acelab portal. You'll get an email about any new conversations that are made, so you can respond directly to those emails. You can also communicate directly through Acelab. If you go to this little conversation icon at the top here, that'll take you over to all of your conversations. So it's a great place to come and keep your product research organized along with your collaboration with different vendors. So if you have any questions about this, I'll share my colleague's meeting link in the chat. You can sign up for a free quick demo with Acelab to learn some more. That'll also help you gain some access to specialized onboarding, some of our early access tools. So folks who are interested in getting onboarded with some of our newer tools can let us know and we'll get you all set up with schedules. Our team will help you implement this and onboard you onto this so that you can really keep a comprehensive firm library of product information stored on Acelab that's fully collaborative with your team and with different vendors as well. All right, other than that, a few housekeeping items from me. Really want to encourage folks to ask questions and send some comments during today's presentation. We'll be keeping our eye on that throughout the webinar. We should have some time to get to questions live at the end of today's event. And if we don't get to your question, we will follow up with you after the webinar. Other than that, for anyone who's looking for AIA credits or CEUs, today there's going to be a QR code at the end of the presentation. So you'll just need to scan that to sign up to receive those credits. So be sure to stay tuned to the end to make sure that you can access that QR code. All right, I think that's it for me. Andy and Rick, whenever you're ready, feel free to go ahead and get started.
Great. Thank you so much, Bo. And thank you to everybody who's on with us today. My name is Rick Kile. I'm the Director of Green Amenity Business for Siplast. What does that mean? It means I manage our vegetative roof and overburden program. Siplast is a roofing and waterproofing manufacturer. Pride ourselves in our technical expertise in our premium membranes and complete assemblies for the total building envelope. Joining us today is Andy Watts with our building roofing science team. Andy, can you give a quick little introduction of yourself?
Sure. Also, do you want to reshare the presentation, Rick?
I do want to reshare the presentation. Thank you.
Excellent. My name is Andy Wagner Watts. I am the Building Science Education Manager on our Building and Roofing Science team. I've been in the construction industry for over 15 years, working in everything from waterproofing and transitions and sealants and air barriers and insulation, all of those fun things. I also have the pleasure of co-chairing the Air Barrier Association Technical Committee and involved with a number of industry associations. Thanks
Great.
for joining us today.
Thank you, Andy. So we'll get rolling. Before we get off of the title slide, extra credit today for anybody who gets the when green turns to blue reference. I'll give you a hint. It is not related to stormwater. So there you go. Learning units, as Bo mentioned, I'll just reiterate, there's a QR code at the end. We've recently transitioned our CEU credits over to BNP Media. So you have to do the QR code, very quick registration, just to make sure you get your credits. And I'll leave that screen up at the end. You know you're here for about 45 minutes. There'll be opportunity for question and answer at the end. We'll do our best to facilitate questions as we go through the presentation as well. So today we're going to learn about some of the challenges unique to meeting stormwater management requirements. We'll identify some of the tools that we can integrate into those overburden assemblies that you already specified to help meet those stormwater management requirements. We'll discuss some design considerations that not only have to do with the actual stormwater itself, but building envelope, things of that nature. And then we'll understand the implementation of some of these tools via a couple of case studies. Easy for me to say. So I thought this quote was pretty poignant. And basically, the EPA has identified urban runoff and storm sewers as a leading cause of impaired water quality. So it's a significant problem. And really, those of you who might be on the call from New York or the greater tri-state area, this is pictures that you might even be familiar with from last year. And really, the issues that we're continuing to see increased volatile storm events, significant storm events that are having this kind of effect on our urban areas. We just had two, I kind of see, this post was from Halim Lee on LinkedIn. And coincidentally, obviously, in the last couple of weeks, we've had two significant hurricanes in the Southeast as well, wreak havoc. And unfortunately, this seems to be the new normal, is these significant storm events at greater regularity. You can see this infographic here, U.S. flooding risk in 2020, so 4 years ago, and how this is projected to increase by 2050, just in terms of the number of events per year. And so the area and the affected areas is about the same, but the timing and the frequency at which we're going to see these events is continuing to increase. I think we're already seeing the effects of that right now. Looking at it another way, how what kind of cost effect does this have on the general populace, on the country as a whole? Significant change in the cost that the damage that these storms can do to our populations. Excuse me. So what's the problem? Really, the problem is that retrofit storm sewer upgrades are expensive and they're disruptive in terms of construction, and they're not, frankly, as highly prioritized as major stormwater projects like roadway, bridge, or culverts, or things of that nature. Furthermore, in our major urban areas that have experienced flooding historically, there's a general acceptance that this is kind of normal and okay, or business as usual, as the original quote states. So what's the problem? The problem is a couple-fold. It's the capacity issue. So at the time that these drainage systems, these stormwater systems were developed, we had more pervious area and less building, and as our urban areas have continued to grow and expand, so has the impervious area. And so those existing stormwater infrastructure are managing more and more stormwater year over year. Additionally, it's aging, so it's not getting any younger. A lot of infrastructure in the country is unfortunately in disrepair, and our storm systems are no different. And then lack of maintenance. To keep anything running efficiently, any kind of working system, building system, infrastructure system, there needs to be a maintenance program. And frankly, there just isn't adequate maintenance for the sheer number of volume of stormwater infrastructure. So, which can lead to clogging, can lead to damage elsewhere. Another challenge that's kind of unique to the United States just because of the expanse of the country and the size of the country, is how different municipalities handle stormwater, and rightfully so, because Seattle, Portland, and the Pacific Northwest have very different rainfall, very different stormwater challenges than the desert Southwest, than does perhaps the Southeast, or the Northeast. And so we have significant different climate regions across the United States, different levels of precipitation, and then how we manage that stormwater respectively creates a challenge. Not so much for the individual municipality, but this really highlights the importance of tailored stormwater management per municipality or for that location, to deal with their specific challenges. Where that becomes challenging is for us as specifiers in the construction world, and understanding, making sure we have a clear understanding of what's required in what municipality, to help achieve those stormwater management goals. So again, the challenges: water quality is certainly a component. It's a measure of how suitable water is for a specific use, based on chemical, physical, biological characteristics. But flooding in particular usually has to deal with volume. So we manage stormwater in two ways commonly: so retention and stormwater detention. I always make the bad analogy that if you have trouble remembering which one it is, when I was in high school and would get in trouble, I would go to detention, but the school would eventually let me go home. So detention, we're storing water for a period of time, and then it's released out into the storm at a prescribed rate. Retention is if the school kept me forever, which I think sometimes my parents would have liked, but not necessarily the case. So retention with regards to, Andy's already shaking her head at me. Stormwater retention, holding that water, reusing it in building systems, not releasing it out into the storm at all. So let's take a look at some stormwater management solutions, how we can, some of the tools we have. So traditional at-grade stormwater management solutions. So detention retention pond. This is a common solution utilized in more rural areas, more urban areas, or less urban areas where we have more access to land, inexpensive land perhaps, and water can simply be put into these retention ponds, or a detention pond, and either released or held and then infiltrates into the groundwater or evaporates, right? Planters, it can start to get a little more urban, little more density, but planters where we can hold water for a period of time, usually at grade. We can start to elevate those over structure, but then they really do start to become more expensive. And then commonly in our urban areas, we do see detention tanks. And these are usually located in the basement or at the first level of a building, just because of the sheer weight. You can see a picture there from highlandtank.com that shows a couple of detention tanks, and just getting an idea of the scale of those things is, that's probably taking away from some parking or potential retail space. But what about managing stormwater on the rooftop? So by moving the stormwater management to the rooftop, we free up space at grade or in the basement that could be used for parking revenue or perhaps retail space. Costs, perhaps in the municipality you're working in, stormwater management objectives can be subverted, but there is maybe then a fee incurred to do so. So by managing it still on the structure with other constraints, we are eliminating those fees potentially. And then creating additional usable space. So again, over structure, if we're perhaps managing the stormwater beneath a walking surface, some sort of hardscape, within stormwater planters on the structure, as part of an occupiable space on a terrace, a plaza deck, something of that nature, we're getting a multitude of benefits and not just finding a place to park that water. But managing it in the green roof. So, this is a great image from Living Architecture Monitor from Green Roofs for Healthy Cities, and it speaks to the volume of benefits that come with vegetated roofing. And there are great environmental benefits. So we're talking about urban heat island effect, which I'm guessing most people by now are familiar with that concept, but the fact that our rural areas are typically lower temperature than our urban areas, and due to impervious surface largely. And so if we start to green up some of that impervious surface with vegetated roofing, other landscape on structure, and we start to bring down that ambient air temperature, creates a healthier ecosystem for us all to exist in. We also recreate habitat, so largely your birds, butterflies, bees, pollinators, but things that are really critical to a healthy ecosystem, and then improved air quality. Social benefits, we start to get into some of those things that make dollars and cents, right? Increased usable space is critical, especially in major urban areas. We've paid for, potentially a lot line to lot line development. Where can we add increased usable space for not only community, but interaction, elevated living experience, which can translate to dollars and cents for a building owner. Biophilic design is another term that you're probably hearing quite frequently now, but it's not a new term. It's a term that dates back to the 80s, and there are studies in the 80s that show you that integration, so biophilic design being the integration of nature into the built environment, and biophilic design can actually aid healing times for patients in hospitals. So taking say a green roof or green wall, bringing that into a space, reducing the healing time by up to 20%. I mean, think about healthcare costs and how that affects not only our society, but at an individual level, how impactful that can be in our healthcare system. And then economic benefits. We do get some energy efficiency from a green roof, not a whole lot, and unfortunately, there's not a lot of code that will allow that. We get an R value of 1 to 2 per inch of depth of growing media, and then increased membrane life expectancy, which is a huge benefit for an owner. Number one degrader of roof membranes is UV, and so by protecting it with overburden, it does allow us to get a longer lifespan out of the appropriate membrane for the appropriate project. But all those, in addition to stormwater management, which is what we're talking to today. But we want to qualify that, right? Building on top of structure, but be it a vegetated roof, pestle paver deck, can be more expensive than doing similar type applications at grade. And when we're talking about stormwater, that's also the case. And so I don't think it's managing stormwater on the rooftop is a great solution. It's not applicable to every project. And so if we have the opportunity to manage stormwater in the landscape, you're probably going to do that first. It's least expensive, via that detention or that retention pond. If you have it under hardscape, if you have parking adjacent, perhaps you have the opportunity to integrate porous pavers, detention space below those porous pavers. Vaults or detention beneath the footprint of the building, certainly a possibility. It might come at the cost of parking or some other things. But ultimately, if those three are not viable, we can start to look at the roof. Or if you already have a vegetated roof on the project, how do we go ahead and turn that into a stormwater management tool where you're using the benefits of that to offset other costs associated with the building? So again, qualifying the project, are we in an urban environment? Most of the time, we're going to manage stormwater on the roof in an urban environment where we have lot line to lot line or limited at grade space. Do we have high groundwater? High groundwater is extremely expensive to excavate around and navigate around in construction. And so maybe we don't have the opportunity to store those detention tanks in the basement. And then it starts to take into space at grade. And we probably don't want to do that. That's high value retail space, high value per square foot. Is it a sloping property? Usually on sloping properties, only our lowest point can be used for managing the stormwater. So that creates another challenge. Is it a brown site? So excavating, again, a brown site and having soil remediation can be very costly to a construction project. So these kind of criteria or any of these things affect your project, perhaps managing it on the rooftop is a possibility. So the solution, is a vegetated roof the solution? This is local law 9294, AIA in the tri-state New York area. Probably familiar with this by now, but requiring green roofs or solar on all new construction, and then all significant re-roof or repairs as well. And a component of this is managing stormwater. You see right there in that red box, an additional 1 million gallons of stormwater managed each year. Potentially we can do that, but most extensive vegetated roofs, they'll manage stormwater via retention, but they won't manage enough stormwater. So we haven't created enough space in your typical, 4-inch vegetated roof profile to manage enough stormwater. And that's because most vegetated roofs, you see here on the left under retention, that's about all the stormwater they're gonna manage. So you're retaining water within the depth of the media profile, and you're retaining water in the drainage and retention component. Or, if we've added a layer of mineral wool or another retention layer, you have like a retention fleece, you're managing water in that and in the media profile. But that's it. There's no detention to be released slowly off of the roof. We need to integrate other components to do so. One of those is purple roof, other are blue-green roof concepts. And it's really about tools, right? If we think back to that map of the United States and how climate varies across the country, our precipitation volume changes across the country, varies across the country. It's about how do we take these tools and integrate them into the systems we already specify. So it's not a one-size-fits-all solution. So purple roof concept is one of those tools. It can transform extensive vegetated roofs into detention-based roofs by integrating a couple of additional layers. So we see here we have a traditional extensive vegetated roof profile in the top, and then we have some plant material, we have some growing media, but then we are introducing a layer of mineral wool, which acts as retention. We're adding a layer of honeycomb, which is our detention, or our layer where we're going to hold the water. And then we have a detention mat, which is going to slowly release water laterally. That detention mat has thousands of threads per square inch, and it releases the water slowly via friction. But that honeycomb layer is really the critical layer in that it compartmentalizes the water so that this can be an effective solution on low sloping roofs, which is very unique to purple roof. That honeycomb layer is where we're going to park the water, where it slowly draws down until it can be released off of the drain. So we're really reducing that peak flow off of the rooftop to where we're not surcharging our existing storm and creating that kind of instantaneous flooding, but it's drawing down over a 24, 48-hour period, and this can all be modeled to a specific project. A blue roof or a blue-green roof is another potential solution. We're taking an extensive vegetated roof, or we could create this space beneath pedestal pavers. And again, we're creating a space to park water. So you can see that structural voiding unit there. This happens to be an inverted roof membrane assembly. So we have membrane down at the bottom, an extruded polystyrene, and then we have our structural voiding unit, which is going to hold the water until it can be slowly released off of the roof. And these are beautifully simple in that they're just combined with a flow control drain. So pretty standard drain body or standard looking drain body, but the flow control drain does a couple of different things. But you can see extensive vegetated roof plus a structural voiding unit gives you the blue-green roof. Same thing underneath pedestal pavers. So if you're specifying pedestal pavers on a project already, you have annular space typically between top of membrane and bottom of paver, or if it's inverted, top of extruded polystyrene and the bottom of the paver. That space can be utilized to store water if you pair it with a flow control drain. And
Hey,
so,
Rick.
Yeah, Andy.
We have a question that came into the Q&A asking what type of time delay is provided between the precipitation and the discharge.
Yeah, so that's going to vary depending on the project and how we've designed it. Usually, and you'll see in the case studies later, there's a prescribed release rate. So when I talk about parking water, we're creating a space for that water to build up that's required by the municipality. So it's that volume requirement. And then there's a prescribed release rate along with it. And so we're usually monitoring that at the drain via that aperture. So you can see up on the screen right now, there's a flow control drain. And thank you for the question, and thank you, Andy. There's a flow control drain, standard drain body, it's 4 inches, but there's actually a standpipe there, and then there's an aperture drilled in it. And so this is going to control the amount of water, and that's dictated by usually the municipality in conjunction with the civil or the MEP that's going to actually size that to make sure that we're within that release rate limit. And then the top of that standpipe acts as an overflow drain. So this is a project in New York that we'll showcase later, but shows that assembly being built, right? So you can see the structural voiding unit on the ground, and then the green roof is installed over the top. Another potential configuration here is a passive irrigation blue roof. So this is a retention ability. So a lot of the components are similar here in the way that we build it, but this is to hold water long term. So if we're going to do this, we can't really include extruded polystyrene in the conversation. That would need to happen below the membrane or in another configuration. But we would hold the water indefinitely, and then it's used via capillary action to irrigate the green roof or the planter. This is a configuration that's used commonly in the city of Los Angeles and other major municipalities that have retention-based requirements instead of detention-based requirements. So we're finding those places to park water. So design considerations, where I hand it off to Andy. Andy, take it away. Just let me know when you want to.
Okay, let's click over to the next slide. As we jump into all of the different considerations that go into designing these roofs, I have a question for you to start. In your opinion, what is the most important component of the overburden roof assembly? You can put it your answer in the chat. You can put it in the Q&A box. But what, for you, do you feel is the most important component of these assemblies? Because ultimately, I do believe that we need to look at all the parts of this sandwich, of this roof assembly, of this roof sandwich, from the structural deck all the way up to the exposed surfacing, everything in between. However, I see some things coming into the chat. We have waterproofing, we have drainage, the roof membrane.
People are getting this right.
Yeah, and I completely agree with those comments, because no matter what we put on top of our roof, the number one priority of the roof is remaining the same. Whether it's a traditional roof or an overburden roof assembly, we are trying to keep our buildings warm or cool, depending on your climate, and dry. So we need to look at all the components with an eye to evaluating what is the best choice for the membrane in this roof system that I'm designing. So let's click over to the next slide and we'll talk about what those options are. I am a firm believer that every roof membrane has its place, but we have to pick the right one for our roof. So when we are evaluating these membranes for overburden, it is recommended to evaluate how the system is going to perform, not only as a roof, but also as a waterproofing membrane itself, because it is going to create that bathtub on the top of our roof and have to stay watertight under a potential decent head of water. Now, if we start all the way over on the right side of your screen, we're going to work our way kind of backwards, I guess, the way we read, with thermoplastic and membranes and thermoset. So thermoplastic membranes are your PVC and TPO. Thermoset membranes, the most common is EPDM. All of them are classified in that single ply category. They are manufactured in a factory to be watertight. They come in big, wide rolls, which allows us to cover big roofing areas very quickly. They don't have a lot of seams on the roof comparatively to these other technologies, but then we seal these seams either by heat welding, if it's a thermoplastic membrane, or using some sort of tape or adhesive if we're using a thermoset membrane, to create an impenetrable lap when it's done properly. Now, these membranes as single plies don't typically allow for a lot of redundancy. especially when we come to our flashing detail configurations at our interfaces, at our drains, that are more commonly associated with the other types of membranes that we're going to talk about. And even though we have heat welded or taped these seams, the laps are comparatively narrow to the other systems we're talking about. So even a minor breach in these seams could allow for moisture migration beneath the single ply that can be hard to detect or repair when it's all the way under all these other layers in these overburden assemblies. And this is true whether we're mechanically attaching these systems or adhering them. The weakest point in any assembly is where two things come together. And that's true all the way around our buildings. Next up, we have PMMA, which is a liquid applied membrane. These materials come to the job site in a liquid form. They come in two different parts that are then mixed together. The liquid applied polymer is installed on the roof with embedded polyester fleece in the middle to give it its strength, and creates a membrane that can be either applied to horizontal or vertical surfaces. So if we create our bathtub, we can go all the way up the sides with the same membrane, and it can form a seemingly unlimited number of detail conditions and configurations. Now, PMMA is known for its rapid cure time, which allows for us to complete roofs very quickly, or in this case, add additional layers of our overburden assembly, even the following afternoon or day. Now, and it's also compatible with a variety of other substrates, including certain PVC formulations. So depending on what we're doing, if we're doing different sections of our roof in different ways, we do have the opportunity to mix and match technologies if needed when we're using the fluid applied. Now, PMMA, just like every other technology, does have its limitations. It cures quickly, which also means it has a short pot life, which means it needs to be applied quickly after it's mixing. This comes down to the workmanship side of all of these membranes. It can also be a challenge to apply if we're working in high temperatures. Ambient temperatures above 100 degrees Fahrenheit, or when surface temperatures go above 110, things can get particularly challenging. So the installer has to be aware of it. They have to store these materials and handle them properly in order to ensure a quality finished product. Next up, we have hot rubberized asphalt. Now, these systems also create monolithic membranes. They cover a large surface area, no seams, just like the PMMA. But because hot rubberized asphalt membranes are hot applied, as the name suggests, the base asphalt has to be heated with a kettle on site, which can be less desirable for certain building owners due to safety concerns, such as the heat and the odor that comes with it. Not your first choice if you're putting this on an occupied hospital, for example. The odors just tend to be not ideal. Now, because the material is soft following application, it does have to cool. It can be susceptible to mechanical abuse unless it's protected properly. But we do still see this being a very popular option in some parts of the country. I think there is, with each of these technologies, a very regional mentality to what is used in different parts of the country, and what the contractor force is familiar with. And then finally, we have our modified bitumens, or ModBit. SBS ModBit membranes are thick. They are pre-manufactured sheets that are applied in a multi-layer redundant configuration, which you can see in the picture all the way on the left there, which allows for a more conservative double layer of protection during the installation process. And when we get this all built up with multiple layers plus the overlaps, in most parts of the roof, you have several layers of protection. Now, because each layer is independent, they can be applied separately. So we have a base layer of our ModBit system that's applied, and then we come in with a cap sheet. This allows for phase construction and gives the contractor the ability to dry in areas of the building quickly, and then come back and do that final part of the roof if there's a better time based on sequencing of the whole project. SBS membranes can be applied in a number of different ways. We have torch applied, which is one of the most common methods for waterproofing installations, but they can also be applied with cold applied adhesives or a hot rubberized asphalt mopped on adhesive as well. Now, this is not a fast application because we are putting it on in multiple layers, and depending on the application method, it can take more time compared to the other systems. And a torch applied application does have an open flame. So again, something to consider based on the requirements of the building owner and the other entities working on this project. Now, once we get our membrane squared away, we pick our poison there, we're going to start building up our roof. So if we look at the next slide, we're going to talk about the insulation types. There are 4 main types of insulation used in roofing. We have polyisocyanurate, extruded polystyrene or XPS, vacuum insulated panels, and then finally expanded polystyrene or EPS. I'm going to talk about them in a slightly different order than we show them on the screen here today, because we're going to start with the most R value per inch, and that's the vacuum insulated panels. These are clearly first when it comes to R value per inch. It's also clearly first and the most expensive because of the R value per inch and how they're manufactured. Now, vacuum insulated panels have an R value per inch nearing R30, which is crazy. But they are limited because they cannot be punctured or cut on site. These are manufactured. If they are cut, if they are punctured, their R value goes to a nice big fat round 0, which is quite lovely. Now, so because of that, we have to protect them, typically using some sort of polystyrene, typically XPS, and then we use the XPS around non-square areas, around penetrations, protecting the top and bottom of the panel. So there is a craftsmanship into how we lay out these panels to do it effectively. Next up is polyiso, which has an R value per inch about 6.5. It is more cost effective by far than the vacuum insulated panels, and it can be cut on the project site for ease of installation. Polyiso in roofing in general is the most common type of insulation. The problem when we talk about overburden assemblies is that it cannot be installed on the wet side of the membrane. So we need to understand, and we'll talk about how we put these pieces together in the next few slides. Next up, we have XPS or extruded polystyrene with an R value of about R5, which is just below polyiso. The benefit of XPS is it can come in a very high compressive strength, which is really helpful when we're stacking things on top of it in overburden assemblies. And it has a very low vapor permeance, making it well suited for going in places where it can get wet. So being able to put it in the wet part of our roof assembly provides us some flexibility. And then finally, we have expanded polystyrene or EPS, which has the lowest R value of the 4 types. EPS, if you're not familiar with it, is the type of insulation that appears to be made of little plastic balls that are all fused together. It doesn't appear, that's exactly what it is. This material is very lightweight. It can be very cost effective. However, it will absorb more water than an XPS, making it less of an ideal installation for the west side of your roof membrane. Still can be used, though not as recommended as the XPS. So if we go to the next slide.
Yeah, I would just add that,
yeah,
you know, it's they're all different tools, right?
Yes.
We're trying to achieve, and every project's a little different. Our objective is a little different, and so they're different tools to achieve our insulation value. In stormwater management, that's certainly going to guide us towards, you know, a couple of these solutions versus others, and just like with the membranes.
Oh, 100%. Thank you. So why are we talking so much about the wet side of the roof membrane? Now, this is a conventional roof assembly for an overburden roof. You can see that we have the insulation installed directly on the roof deck, followed by a cover board, our waterproofing membrane, and then we build up our overburden assembly on top of that. In this case, we show our root barrier, drainage, growing media, and vegetation. The challenge with this assembly is that there is a cavity formed by that insulation where water can potentially travel below the membrane and not drain out properly. So we have that extra space between our roof deck and our membrane that when we're starting to store water can potentially cause us to ask some questions. Now, you can see here that we list slope as a benefit of this assembly. The benefit of putting your insulation on the bottom is that you, if needed, you can use the insulation to create a slope in a low slope roof assembly, either using tapered insulation or by sloping the roof deck. I put that in there with a caveat, and you're gonna find out more here in just a little bit as we talk about the impact of slope on these blue and blue-green roof assemblies. So so let's talk about slope. Slope for a blue and blue-green roof may not be a good thing. A zero slope roof deck actually allows for more storage of water and evens out the distribution of the weight across the roof when it is fully loaded. In this example here, we're comparing a zero slope roof deck holding a 3-inch of water maximum to the same size slope roof at a 1/4 inch per foot slope and the same maximum water depth of 3 inches. So if you click over, this is the side view. Let's look at it, see what it looks like from the top. And you can see here that due to our 3-inch maximum water depth at the deepest point of the water, if our slope of our roof is flat, we can actually increase the storage capacity by over 65% compared to if we are trying to slope to drain like you would try to do in a conventional roof without the overburden and without that storage. When we are sloping our roof deck, we also have to take into account higher finished elevations at the top of that roof slope, which may lead to higher parapets and other design factors that ultimately change the look and potentially increase the cost overall of the roof assembly. We're making these assemblies thicker, and so it's a much different conversation when we talk about overburden. It's also important to recognize that a flat roof is only possible when we're using a true waterproofing membrane. Single ply membranes, the thermoplastics and the thermosets, do not typically allow for application on a completely flat roof. They require that integrated slope either from the roof deck or the insulation in order to allow the drainage. They just can't handle being that bathtub. So again, it goes back to choosing the right product for the right application. Yep, you're good. So another way to do that, another way to build these roofs is called an inverted roof assembly or an IRMA. The benefit of this assembly is that the membranes are well protected below the rest of the roof, and it's protected from damage by the insulation. So we reduce the risk of water penetration due to damage over the life of the building. The challenge with an IRMA roof is that XPS really is going to be the best insulation recommended due to its ability to withstand moisture. So we've taken away some of those options for insulation if that's an important factor for your project. However, XPS is light, and so we're not adding a lot of extra weight, but that means we also have to make sure we have enough weight on top of it to prevent buoyancy so it doesn't float away. Next slide. In other words, we need to prevent having a floating raft on top of our roof, right? So even better. So in order to do this, insulation manufacturers are going to publish the ballast weight that's needed to ensure that the insulation isn't going to float away. So you can see this chart here, a credit to DuPont. You can see how much ballast is needed when you have a fully soaked piece of XPS insulation. This is a case where a little math can go a long way to solve a big problem.
When we think about that, so
go ahead.
Oh, I was just gonna say, if we think about, our value requirement being 30, that's 6 inches of traditional XPS, and it's 45 pounds. So there's a significant ballast weight, and so that does end up becoming a significant consideration where in a condition where we might be super saturated or fully submerged over 24 to 48 hours.
Oh, 100%. as we get these big storms coming in, right?
Exactly.
So that brings us to the discussion of weight. Rick likes to weigh things in milk jugs.
It's the only way.
So it's the only way. Um, so 1 cubic foot of water is approximately 6 gallons of milk, just under. Most municipalities with stormwater management requirements are requiring that systems store between 2 and 4 inches of water. That can be nearly 21 additional pounds of loading on your roof. And then we add to that buoyancy offset weight that we just talked about, and we're starting to get things to be pretty heavy. So we're needing to really rely on that structural engineer to make sure that our roof can support all of that. Yes, so when we're storing water on the roof, there are other considerations in addition to the main assembly, and that's our transitions. It's not only the how are we transitioning to our other assemblies of our building, but the where, including our wall WRB transition, any fenestration, such as access points on the roof. And when we're designing these transitions, we need to be concerned about not only the adhesion and the compatibility between components, we also need to make sure that we're keeping our bathtub tight. And this means that the transition has to be above the elevation of the overflow drains. While the roof membrane is designed to hold water, these other membranes and flashing components may not be designed to withstand that water head. So the next slide is going to show us a detail of what that looks like. And you can actually, we have this dotted line coming across the cross-section detail on the left. And that's where the point where our overflow drain is located. And if you follow that line across to our rising wall detail, you can see that in this case, we're making sure that that dotted line is falling below the point where our roof membrane ends. So where we transition to the wall membrane, our through wall flashing, all of that is happening above the point where we expect water to sit and to stay. Transitions between assemblies are the weakest point in our building regardless, due to material interfaces and trade interaction. It's important to be conscious of not putting more stress on them than is absolutely necessary. So with this, I'm going to pass it back to Rick to talk about how we make sure that our water levels don't get too high.
Thank you, Andy. So one of those is making sure that we design for continuous drainage throughout the assembly. So the image top right there, actually we're managing stormwater underneath the pedestal pavers. We're also managing water on the blue-green roof side, which is more towards the bottom or on this side of the metal edge. What we haven't accounted for there is drainage between those two overburden types. And in this particular project, we had all of the drains located within the blue-green roof. And so there would be flow of water when we did have a larger storm event. All of the components are loose laid, so we would expect that water to eventually perk through, but we want to avoid the building up, the damming of water that can displace some of the components and wreak havoc on that overall assembly. So ensuring continuous drainage, open and free all the way through to the drains is critical. You can see at the bottom image, they went through and actually cut in scuppers in at a prescribed rate across all this metal edging. Another way to incorporate that is with scuppers at the bottoms of your built in place, sometimes cast in place concrete walls in between transitions, just ensuring that we're maintaining continuous drainage in these applications to avoid that damming. Some additional coordination points just in the design process. Obviously, if we're managing stormwater on the roof, we're now not only involving architect or enclosure consultant, but civil engineer, structural engineer, landscape architect. So there's a lot of people sitting around the table just making sure that these things are well coordinated. Civil engineer is going to be in regardless because this is something that is done at the permitting phase, right? How are we managing stormwater? Specifications in terms of leak detection, making sure that since we are going to be holding water and we are creating some form of bathtub on the rooftop, that we are ensuring that the membrane remains watertight, or that it's watertight before we go ahead and we start to install the overburden components on top when we have less access to that membrane. So that's called an integrity test, and that can be done in a couple of ways. via flood test, which is more traditional, or more recent, and it's really gained in popularity because of high cost in water and instant results, is electronic leak detection. And the way that that's integrated into the project will really depend on the membrane assembly itself and the technology used. There's also monitoring leak detection, which is a smaller percentage of leak detection projects, but the opportunity or ability to monitor the water tightness of the roofing assembly throughout its lifespan. So just some considerations, but at a minimum, we want to make sure that when we start building these systems on top of the membrane, that we're starting with a watertight substrate. So let's take a look at a couple of case studies. Case study number one is a purple roof assembly at Princeton University, approximately 7,000 square feet. And what's really impressive when you look at the assembly is that we're not integrating a significant amount of extra depth here to manage a really high volume of stormwater. So it provides both retention and detention. And so there's over 1,400 cubic feet of retention, or almost 2,000 cubic feet of detention. So really impressive for this project, again, that they manage stormwater. And we see this curve that I referenced earlier. It's nice to have a graphic to go along with it. The purple or the blue curve is an unmitigated stormwater runoff curve. And so you can see how this would surcharge the stormwater infrastructure at the time of the storm event. And if this building, along with all the other buildings in the same area, are doing the same thing, that results in flooding. By reducing that peak flow and really, as Purple Roof would say, flatten the curve, we're slowly releasing that so that the stormwater infrastructure can manage it in place. You can see that this assembly, they already had a vegetated roof for the project, but by adding an inch of mineral wool and an inch of the honeycomb layer, we're able to manage that significant amount of stormwater. This is pretty reasonable in terms of loading. So typical bare roof, maybe 30 pounds dead load is a number we see a lot. 58 is not exorbitant. So you can see the reduction in the peak runoff there in terms of numbers at the top middle, from 1.39 cubic feet a second to a quarter of a cubic foot per second. So significant reduction there. If we don't like milk jugs, I think, freight line containers is another really good visual. But almost 3 freight line containers worth of water stored, managed on this project. So really, really impressive here at Princeton. Case study number 2 for our Rockaway. This is a scenario where, looking at the project as a whole, it's a highly urban environment. There's a high water table, and because it's New York, they're already required to do a green roof. So again, we're using that criteria to really qualify this as a suitable blue-green roof application. So you can see here in the permitting documents, had to store almost 2,000 cubic feet of water to be released at 0.62 cubic feet per second. So that kind of goes back to the earlier question that was asked. How are we determining what rate this is coming off of the roof? It's not a one size fits all. It's really, these systems are really tailored to the specific project. There's calculations run in the development process to help do it. So that's going back. It's about 2,000 cubic feet, about half of a tanker there, or 14,558 gallons of milk, if we like the milk analogy better. If you're going to have that much milk, you might as well have some chocolate chip cookies, right? I can hear the laughter coming in, even though it's silent. Looking at that assembly as a whole, we have a substrate, there's a waterproofing membrane, extruded polystyrene, structural voiding unit, and then our green roof assembly over the top, marrying that with a flow control drain, which we discussed earlier. We have a couple in progress pictures there. So for anybody who did not get the reference, which I'd imagine is probably not most of you, it is from the When Blue Turns to Gray, which is a Rolling Stones song from the December's Children's album in 1965. So how's that for an obscure reference? Hence the Mick Jagger, for any of you Stones fans out there. But what's our wrap up? Stormwater management requirements vary region to region, project to project. There's a lot of different ways that we can look at managing stormwater on the rooftop. It's not for every application, but it's worth evaluating when we have some of those things like high water table, brown site, constrained lot line to lot line development. I think if you're already going to have a vegetated roof on it, either because it's part of the design criteria of the project or it's municipality mandated, I would always reach out to a manufacturer, be it Siplast or somebody else, and have them run the stormwater management calcs for the green roof at a minimum, because you can start to offset some of the sizing of your detention tanks or other methods. So you might as well get credit for it, but it's got to be identified early. And if it is going to manage all of it, again, involved early, let's run the calcs, let's see where we stand. There's a number of different technologies and a number of ways that we can achieve that. And let's keep in mind the special design considerations when we're doing it to make sure that these projects are successful. Just a recap on Siplast, total envelope provider. Our the foundation of our business has been SBS modified and PMMAs. We've really expanded into a number of different premium membrane technologies, best suited to the building. Like Andy spoke about, I think it really, if there was one type of membrane for every application, there'd only be one type of membrane on the market. Understanding that, whether we have the structure itself dictating what technology we go with, or the overburden from the top down, there's a number of considerations as to where we meet there in the middle and what's best for the project. And so we have some good solutions there, abilities to help you design these systems, run calculations for stormwater management. And with that, we'll do our best to answer any questions. I see a few more in the chat there. Please click on the QR code, make sure you receive your credits, and we thank you for joining us today.
Awesome. Thank you so much. All right. Yeah, I saw somebody asking for that code, so be sure to scan that before you jump out of today's webinar. Looks like we do have a few moments to answer some questions. Just a notice for anyone leaving, there also will be a quick post-event survey. If you could take some time to give us some feedback on that, that's super appreciated. All right. Do you want me to just start off with one of these here?
Yes, that'd be great.
All right. Let's see, from Dave, as a 2-inch max overflow scupper is required on a flat roof? Question mark. I guess, is a 2-inch max overflow scupper required on a flat roof?
I'm going to go ahead and take a guess that that's partially because of an experience he had on a project, and I'm not sure where that municipality is. I believe that type of code is probably a little regionally dependent, and in my experience, we're not always required to do an overflow scupper as much as we make sure that we have an overflow drain, or if we saw in the case of the blue roof, flow control drain, the overflow on the top. So as long as we have some solution to prevent an overflow condition from happening, I believe that would be acceptable. But Dave, if you want to shoot me an email separately, we can go ahead and talk about that further.
All right, awesome. See, from Denny, polyiso outgasses and loses insulation value. How is this addressed? Andy,
you want to jump in on that one?
Sure. So any type of foam plastic insulation that has a blowing agent is going to off-gas over time. If you are concerned about long-term R value, the first thing to do is to pay attention to your LTTR and design using that. It should be published by your insulation manufacturer. The amount of change over time is going to be manufacturer dependent. It's going to depend on the facer on the product and how it's actually manufactured. So ask the question of your manufacturer to get specific data if that is a concern.
All right, and it looks like there's one left. I see, Andy, that you are working on typing out an answer for that. So
we can answer this one live.
Okay.
Related to, I'm going to pose this. We can pose it to Rick if you want.
Yeah. It's kind of twofold. One is redundancy in scuppers, right? We're not relying on one scupper, one weep to go ahead and convey all that water, because some blockages is likely to happen. However, if the system is installed and the assembly is installed as it should be, minimal waste, all the Coke bottles and cans are taken off the roof during construction, the layers of the vegetated roof, or like the filtration layers, the drainage layers are installed correctly, overlapped correctly. Any of that overburden, like growing media plants, is going to be captured within that and not migrate its way through the assembly. So those two factors should provide for enough drainage in the scuppers over the life of the project.
Awesome. All right, with that, looks like we are all wrapped up. So if anybody has questions, feel free to grab the link from the chat to get in touch with Siplast or leave them on our post-event survey. Thank you so much to everyone in the audience for attending today. And thank you, Andrea and Rick, for a great presentation.
Thanks again,
everybody.
everybody. And thank you, Bo. I'll go ahead and leave this screen up for, I don't know, another 5 minutes or so, just in case anybody's having a little challenge registering.
Okay.
Please feel free to reach out to me directly at the email if you're having difficulty or can't scan, and we'll make sure we facilitate the credits.
All right, sounds good. Yeah, feel free to reach out if you've got any problems with that. I am gonna leave the webinar. Hopefully it'll leave you guys on so that folks have a few more moments with that code.
Okay.
All right, thanks everyone.
All right, thank you.